Hi friends, let us do some problems today. So our first problem is here. For a reaction 2A plus B giving C plus D, if the rate of consumption of A is 0.1 mole per liter per second, the rate of production of C in mole per liter second inverse is. So as you can see, the reaction is 2A plus B giving you C plus D. Writing in the differential form, we can write in the differential form as minus 1 by 2 d by dt of concentration of A is equal to, since this is the reactant, we are giving a negative sign here, and since two moles of A are reacting in the differential form, you have to put the minus 1 by 2, which will be equal to minus of d by dt of concentration B should be equal to, now since it is on the product side, this will be d by dt of C, and again this will be equal to d by dt of D. So what will be the, it is given in the problem that the rate of consumption of A is 0.1 mole per liter, and the question is what will be the rate of production of C. So that means we can equate this one and this one. So what it will be, minus 1 by 2 d by dt of A will be equal to d by dt of C, or dc by dt will be equal to 1 by 2 into this one, d by dt of C will be equal to 1 by 2 into 0.1, which will be equal to 0.05, and the units will be mole liter minus 1 second minus 1. A very simple problem. Thank you. Our second problem is on the rate of reaction itself, but it is for a gaseous reaction. So we can see the problem. For a first order reaction, A in the gaseous phase giving you 2B plus C, both all are in the gas phase. Find an expression for the rate constant in terms of initial pressure P0 and final pressure at time t, which is P. So let us try to solve this equation. Our problem is A in the gaseous phase giving you 2B plus C. As we know how to solve this. So this is a gaseous phase reaction in which the pressure is given as in terms of or in place of concentration. So at time t, time t equal to 0, our pressure is given as P0, which is the total pressure. And now at time t equals t, our pressure is P. So how to solve this? At t equal to 0, let us see what will be the pressure. So at t equal to 0, the total pressure will be the pressure of A only, since the reaction has not been started, and only A will be constituting for the total pressure. So at time t equal to 0, the total pressure is P0. At time t, x moles of A would have been reacted to give you 2B moles of B and C moles of and 1 mole of C. So how to write the remaining terms, which will be at time t is equal to t, this A will be P0 minus x, whereas 2B will be 2x, and whereas C will be x. So at this time, what will be the total pressure? The total pressure Pt will be equal to P0 minus x plus 2x plus x, which will be equal to P0 plus 2x. Now you have to get an expression for x. So x will be equal to Pt minus P0 by 2. Now it is given as the reaction is a first order reaction. If the reaction is a first order, we can use our first order rate constant, which is first order rate equation, which is K equals 1 by T log of, normally we used to write A by A minus X. So this is A by A minus X. Now our A is nothing but P0. Instead of A, we can give as P0. And instead of A minus X, we have to find an expression, A minus X. So A is P0, P0 minus, what will be X? X is equal to Pt minus P0 divided by 2. And this upon simplification will be, this is P0 minus Pt by 2 minus P0 by 2. So there will be 2 P0, P0 and P0, which will be 3 by 2 P0. So this can be given as 3 by 2 P0 minus Pt by 2, or which is equal to 3 P0 minus Pt by 2. So you have got your A minus X also. So upon substitution, this will be K is equal to 1 by T log of P0 divided by 3 P0 minus Pt by 2, or we can write it as 1 by T log of 2 P0 divided by 3 P0 minus T. So this is our rate expression in terms of concentration of gases. Let us move on to the third problem. So the problem states like this. A wood specimen containing C14 taken from an ancient panel shows 24 counts in 3 minutes per gram of carbon in a detector. However, a fresh wood shows 52 counts in 2 minutes per gram of carbon. Assuming no background signal in the detector and half-life of C14 as 5730 years, calculate the age in years of the wood specimen. These type of problems are very common. And here, as we know, radioactive disintegration follows first order kinetics. We can go with the first order kinetic equation. And also, one another thing we have to take into account is here the activity, or sorry, the concentration is related to the counts. So the counts is instead of concentration. Let us see how to solve this problem. We know the equation of first order rate constant, K is equal to 1 by T sorry, 1 by T log, here there will be 2.303 by T log of A by A minus X. Now here we have to find out the A and A minus X. As stated in the problem, it is given as it was 24 counts in 3 minutes. If it is 24 count, if it is 3 in 3 minutes, if it is 24 counts, in 1 minute the count will be 24 by 3, which is equal to 8. And in the another activity, it is 52 counts in 2 minutes. That is, in 2 minutes it is 52 counts. So in 1 minute it will be 52 by 2, which is equal to 26 counts. Now it is given as the we have to calculate the time t, which is the unknown factor here, but we have also to calculate k to calculate the t. So for a first order reaction, we know k is equal to 0.693 by t half. We should know that this t half is independent of the initial concentration A. So this will be k will be equal to 0.693 divided by our t half is given in the problem as 5730, which upon calculation will be equal to 0.000121 year minus 1. Since it is a first order rate constant, it will be in the here minus 1. Now we can directly substitute in this equation. So you should know the time. So we can rewrite that equation as T is equal to 2.303 by K log of A by A minus X. So A is 26, which is the initial count, divided by A minus X is here 8. And upon substitution of K and simplification, you will get T is equal to, it should be equal. You can calculate by yourself. It will come approximately to 9747 years. Let us move on to the next problem, which is based on the second order rate equation. So the problem states like this: the reaction 2NO in gaseous phase plus Cl2 giving you 2NOCl. Let us write the equation first. 2NO in the gaseous phase plus Cl2 in the gaseous phase giving you 2NOCl. Or this reaction is second order in NO and first order in Cl2. So this is second order and this is first order in NO. 5 moles of nitric acid, given the concentration as 5 moles of nitric acid is reacting with 2 moles of Cl2, whereas the reaction vessel's volume is given as 2 dm3. As the initial rate was 2.4 into 10 to the power of minus 3 mole dm minus 3 S minus 1. What will be the rate when 1/2 of the chlorine has been reacted? So, how to solve this equation, solve this problem? So, for the if you take the second order rate constant as K is equal to, here we know the concentration of NO to the power of 2. It is said as second order, and Cl2 to the power of 1. So, in the first one, it comes to be 2.4 into 10 to the power of minus 3. The units we will take later. Now, what will be the concentration of NO and Cl2? It is given in the moles, so we have to convert in moles per dm cube. So, dm cube is 2 dm cube. That meaning to say that at initial level or in the first experiment, we can write it as in the first experiment. Sorry, there is a mistake here. It is rate is equal to K multiplied by 1. So, in the first experiment, the rate 1 is equal to, rate constant will be same in both of the experiments. This is NO to the power of 2 and Cl2 to the power of 1, which is given as 2.4 into 10 to the power of minus 3. And in another experiment, the rate, the second rate 2 is equal to, rate constant is same itself, NO to the power of 2 again, and concentration, chlorine concentration to the power of 1, and what will be the rate of this particular equation. So let us see what will the constant. So we have to substitute here, 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 and here. What will the concentration of NO? We solve here. Concentration of NO will be equal to 5 moles per 2 meter cube. So this will be 5 by 2, which is 2.5 moles dm minus 3. What about Cl in the initial rate? This will be equal to, it is 2 moles, so this will be 2 by 2, which is equal to 1 mole dm minus 3. And these are for first experiment. What will be for the second experiment? For the second experiment, it is said that, what is the question? It is after the 1/2 of the chlorine has been reacted. If 1/2 of the chlorine has been reacted means initially it was 2 moles, then in the second experiment it will be reduced to 1 mole. So the amount of Cl2 will be 1 mole. So we can write as Cl2 will be equal to 1 moles divided by 2 dm cube. So this will be 0.5 mole dm minus 3. Now what will be the amount of NO? Since 1 mole of Cl2 for 1 mole of Cl2 will react with 2 moles of NO. That means if it is 1 mole has been reacted or 1/2 has been reacted means another 2 will could have been reacted. That means it will be 3 moles, 2 moles would have been reacted from NO. The remaining amount will be 5 minus 2. 5 minus 2. So this will be Cl2 second one, and now second one will be 5 minus 2, which will be 3. 3 moles divided by 2, which is equal to 1.5 mole Dm minus 3. Now what we have to do is either you divide 1 by 2, or you can divide by 2 by 1. So upon simplification, the new rate which is rate 2 will be equal to k multiplied by 3 by 2 square multiplied by 1 by 2 square divided by 5k 5 by 2 square 1 square, which is multiplied by 2.4 into 10 to the power of minus 3, and your final answer will be 4.32 into 10 to the power of minus 4 mole Bm minus 3 minus 3 S minus 1. Hi friends, now we will go to another problem which is also an application of second order rate equation. Let us see the problem. It is a second order reaction involving reactants both initially present at 0.1 molar is 20% complete within 40 minutes, 40. Calculate the rate constant, then you have to calculate the half-life, and then the time it would take for the reaction to say 20% complete if the initial concentrations were 0.01 molar. Since it is said that it is a second order reaction, to calculate the rate constant directly we will go to the equation for the rate constant of the second order reaction, which is K equals, we have derived it earlier, 1 by T into 1 by A minus X minus 1 by A. Time T is given as 40 minutes. Now, the initial concentration A is given as, it is 0.1 molar. So, to substitute in this one, you should know the X. X is actually 20% of 0.1. So, this will be 0.1, 20 by 100, which is equal to 0.02. So if x is 0.02, then a minus x will be equal to 0.1 minus 0.02, which is 0.08. So upon substitution, this k will become 1 by 40, concentration of 1 by a minus x is 0.08 minus 1 by a is 0.1, which will come to 0.0625. 0.0625, and its unit will be mole dm3, and this will be in minute units. Now our second one, second division of that problem is to find the half-life of that reaction. To find the half-life, we have already derived in the previous lectures what is the half-life of an nth order reaction. We will go for an nth order one. Half-life of nth order reaction T half is equal to 2 to the power of n minus 1 divided by k n minus 1 and a to the power of n minus 1. So let us substitute if in our case n is equal to 2. If we substitute that one, this will come to be, it will be 1 by k. So upon very easy substitution, this will be 1 by 0.0625 multiplied by A is 0.1, and which will be 160 minutes. 160 minutes. So the second part is over. Now we have to calculate the time it would take for the reaction to 20% complete if the initial concentrations were 0.01 molar. So we can use the same equation. Instead of K, we have to find the T. So it will be, it will be T equals 1 by K. Again, the equation is same, 1 by A minus X minus 1 by A. Now, the new A is 0.01 molar. So that X will be equal to 0.01 molar. Again, it is 20% complete, so it will be 20 by 100, which will be 0.002. Then A minus X will be equals 0.008. Now, upon substitution, T will be equal to 1 by 0.0625 multiplied by 1 by 0.008 minus 1 by 0.01. This will come to around 400 minutes. Maybe you can change into seconds by multiplying by 60, and also here also this 0.0625 is in minute inverse. To convert that into second inverse, you have to divide it by 0.0625, and that value will be, upon simplification, to be 1.042. Again, this will be mole d to the power of 3 and second inverse. 160 minutes will correspond to 9,600 seconds. 600 seconds, and 400 minutes will correspond to 24k seconds. Since it is a second order reaction, you can beautifully see one very important application of second order reaction, meaning to say, here when we are taking a concentration of 0.1 molar, your time to complete the 20% was 160 minutes. Whereas when you are taking 1 by 10th of that initial concentration, the time to complete that reaction has increased to 24,000 seconds. Let us go to the last problem of this section. This is a direct application of our integrated Arrhenius equation. So the problem is like this. The rate constants for a reaction at 300 Kelvin and 350 Kelvin are 8 and 160 mole inverse respectively. The activation energy of the reaction is to be calculated in kilojoules per mole. So directly we know our integrated form of Arrhenius equation, which is log K2 by K equals dA by 2.303, which is the gas constant, multiplied by T2 minus T1 by T1 dA. Now, given K1 is equal to 8, I'm not writing the rate units. K2 equals 160. K1 is equal to 8 at T1. This is T1 is 300 Kelvin, and T2 is 350 Kelvin. A very straightforward problem. So finally, we have to calculate is EA will be equal to 2.303 multiplied by our gas constant you can take as 8.314 joules, 8.314 multiplied by 300 into 350 divided by 350 minus 300 will be 50, and here we will be having log of, this is K2 by K1, so this will be 160 by 8. This corresponds to 20, and finally your equation will be 52.3 kilojoules inverse.